Yes, it.
Okay. I'll review some.
No, here it's like this. I think he has to. Yes.
If you
Okay. So thanks for coming, everyone, both in person and virtually. I'll be talking about FedOpt++, optimization beyond simple minimization, and federation beyond uniform client selection. I'm Pranay, and I'm a postdoc/research scientist at CFA. So I have been told that this is being live streamed on YouTube, and that this is going to be the most viewed YouTube video ever. So welcome to a moment in history.
Could you share the screen? It's in PowerPoint view. Yeah.
So you are saying the
Okay.
Ritam, can you use the mic? The voice is very faint, Pranay.
Okay.
Is this?
Yes.
Then
It is very
visible.
visible.
This is visible.
This is visible. You can just put this. Share the screen.
This is visible.
this is visible.
It was visible.
But it was not in a presentation. It was like it's very
Normal side.
Same. Same.
It is okay.
Oh, yes.
No.
Okay. Sorry about the glitch. So I'll begin with the introduction. So this talk is about big data, and big data is used in a number of applications. For example, facial recognition in your smartphones, or in healthcare, or in e-commerce. But the biggest requirement in big data is data, and lots of data. And data is naturally distributed because it is often collected from edge devices. These can be your smartphones or tablets, or your health devices, or even devices in your home. And then, once this data is collected at the edge devices, it is used to train these machine learning models. But the problem is that all this data is private for the users, so this should not be leaked. One possible solution in this case is, instead of sending all your data from the edge devices to a central location, you instead train the machine learning models on the edge devices themselves. Another reason for doing this is that communication is expensive, and currently the machine learning models are huge in size. So we want to do as infrequent communication with the server as possible. And this brings us naturally to the paradigm of federated learning. So this is a distributed learning paradigm, quite recent, I would say 5 or 6 years old, in which a global model is learned using local or edge device data. There is infrequent communication between the edge devices and the server, and therefore the privacy of the client data is preserved because the data itself is not sent to the server. Also, the data at the clients, as well as the capabilities of all these clients or devices, is quite different. So everyone is using a different smartphone. They might have a different processor, different processing speeds, and so on. So this is a schematic of federated learning. You have a server at the top and edge devices at the bottom. These resemble your smartphones or any kind of device you might want. One possible application is image classification at your local devices. So all the devices have some images on their location, and they want to classify the images. These can be, simple example, cats versus dogs. A more serious application is where your clients are hospitals, each of which has chest X-ray data, and they want to learn a machine learning model which will help them classify these chest X-rays into different diseases. So we will denote all these different clients with different colors. So if your aesthetic sensibilities are hurt by this slide, I apologize, but these colors only show that these clients are different, they have different kinds of data. So this is how a typical round in federated learning progresses. The server selects a few clients, It then sends its global model to all these selected clients. The clients run a few local updates starting from this global model on their own data. And then the updated model are sent back to the server. The server then takes all these different models and aggregates them to arrive at its updated global model. And this ends one particular round of federated learning. In the next round, the server selects a fresh batch of clients and the same process repeats. So essentially, what we are trying to solve with federated learning, optimization bias, is an empirical risk minimization problem, which is simply you have a loss over multiple samples. Here, n is the total number of samples. These will be distributed across devices. AI BI is one data sample, so AI can be a feature vector, BI can be the label. X is the model we want to learn, and N is any appropriate loss function. It can be the LU loss, cross entropy loss, or anything you can come up with. So this here is a loss which the model incurs for this specific data point. And the most commonly used algorithm to solve this problem is a minimization problem. So we use SGD or stochastic gradient descent, in which you start from model X and you take a step in the direction of the negative gradient. Here, eta is your learning rate or step size. M is the small batch size on which you are computing an estimator of the true gradient. So that's why this is a stochastic gradient. Here, this batch size capital M is typically much smaller than your total data set small m. And federated learning, as I said, essentially solves this problem in a distributed manner. So let's look at minimization problems in FL. So you're supposed to minimize a global function f, which is average of n local functions. Here n is your total number of devices or clients, and fi is the loss function of the ith client. So for the image classification example we just saw, this can be fi can be the loss of the model over the local images of each device. For the hospital dataset or the hospital example, fi can be for the ith hospital. What is the loss on what is the classification inaccuracy on its local set of chest X-rays? But the question I ask is it always a good idea to solve a minimization problem? So let's look at an example. Suppose you have a bunch of devices, each of which has some images of animals. Let's say all of them are cat lovers, so they only have images of cats. And the model is being trained to classify images. And then suddenly a user joins who is a dog lover and only has dog images. Now in this case, if you want to maximize accuracy and say you have 100 clients, 99 of which just have cat images, you can get 99% accuracy by classifying all the dog images as cats. But that's not the point. Right? And this has actually happened in practice with Google in 2015, where because their data set was so skewed towards certain races, they classified some human images of certain races as actually gorillas. This again happened with Amazon in 2018, where their AI tool was used for hiring purposes and was biased against women. This happened as recently as 2021 with Twitter also. Let's see another example of this problem. Suppose we have a bunch of hospitals training machine learning models, as we just discussed, and a new chest X-ray emerges, which comes from a rare disease. In this case, if you are just trying to maximize accuracy, you can classify this rare disease as one of the existing diseases, and that can be disastrous. So, a possible solution we propose is, instead of solving a minimization problem, where you try to minimize the average across all the clients, you try to minimize the worst loss across all the clients, so that you impose some amount of fairness across all the clients. And this actually has been done in practice. So Chestford is world's largest chest X-ray data set. It's been collected by Stanford, and it's been used to promote development of better AI models for chest X-ray classification. And the model which actually won this competition in 2020, the first time model, actually developed this exact strategy for minimizing the worst case loss. So the first challenge is, how do we solve Minimax problems in federated learning setting? And the problem we want to solve is this. You have min variable x, max variable y, and we want to solve the average of n local functions which depend on these min and max variables. This is actually a generalization of the problem I just showed you, where you try to minimize the worst loss. Then, with this more general problem, there was an existing machinery of federated learning which was developed for minimization problem. Now there is need to develop the same theoretical machinery for min-max problems. So is there any benefit of running federated learning in parallel on multiple clients? Similarly, how frequently you need to communicate with this between the clients and the server if you are solving this problem. So this is the first challenge I address in this talk. The second problem I address is of client selection. So as I mentioned in the schematic, in each round, the server selects some of the clients and they run the local upgrades. And usually in practice, the clients are available quite sporadically. Suppose you have an application running on million devices. Typically, you can expect to get 1,000 or a few hundred devices at any given instant. However, the current federated learning theory to model this situation assumes that the server can uniformly randomly sample clients from the entire set of clients. So you have this entire set of clients, and you can uniformly randomly sample a few clients out of these. But uniform sampling implicitly assumes that you have all the clients available and you can choose a few whenever you want. But we ask how about if the availability of clients is periodic? There are few clients which are available at few instances and not at the others. So an example of this is a map of the world. The dark region is where there is night time. There is sun in the rightmost, right for me. And usually devices get updated when they are getting charged, which is often in night time. So when there is night time in this part of the world, the devices in this part of the world send their updates. And there is night time in North and South America, the devices there will send their updates, and so on. And further, depending on the geographical location, there will be some variation in the devices. For example, going back to the classification of images into animals example. So, for example, in India, cats and dogs are the most common pets. However, in the US, many people prefer rodents as pets. So there will be geographical variation in the data as well. So how do you model this periodic availability of clients? And on top of that, you have this variation in data according to the geographic location. So this is the second challenge I address. How do we model cyclic client participation? And can we get some benefits over the existing theory by assuming that we have a cyclic client participation pattern? So these are the two challenges I mentioned. We solve min-max problems in the federated setting, and we try to model cyclic client participation in this federated setting. So let's address the first challenge first. This section is on solving min-max problems in the federated setting. So this is a joint work with Rohan, who was a master's student at CMU. He is now at Inworld.ai. Gauri, who is my postdoc supervisor, and Professor Varshney from Syracuse University. He was my PhD advisor. So a one-slide introduction of an algorithm which is used to solve min-max problems. So this is a typical min-max problem. Your function f is actually an expected value over a distribution. So here C belongs to some data distribution D, and yeah, this gives you the function f. So like for minimization problems, we have SGD. Similarly, it is min-max problems, so you have SGDA, stochastic gradient descent, ascent. To update the min variable, you do descent. To update the max variable, you do ascent. So the min variable x is updated by taking a stochastic gradient descent step. the max variable y is updated using a stochastic gradient ascent step. So a typical figure you will see in Minimax, this is a saddle point. So this is a very specific problem, but just for the sake of context. So in one direction, you try to maximize the function. In another direction, you try to minimize the function. Here, eta x and eta y are your learning rates and all your step sizes. And as I said, this is a generalization of SGD. When you have simple minimization, you do SGD. When you have Minimax, you do SGDA. So this is the problem we are trying to solve. We have a global function f, which is average of n local functions, and each of the local function depends on the data set of each individual user. Here n is the total number of clients or devices. The local loss function depends only on the local data distribution di. So once again, let's look at a typical schematic. We have seen this earlier, but just for completeness, we have a server and several heterogeneous clients. In some round T, say 3 users are selected by the server, I, J, K. Here, the model, we get more concrete. Our model is actually both the min and max variables x and y. So Z is a concatenation of these two. The server sends its global model Z to the clients. The clients run multiple updates on it. They arrive at their individual updated models. They send these back to the server. The server takes these, aggregates them, and arrives at the new model. And then the process repeats. So the algorithm we use in this case, as I mentioned, SGDA is for solving simple min-max problems. When you have this thing running on multiple devices, we run something called local SGDA. So the local part refers to the local updates that the clients are running. So yeah, you have n losses. F is the global loss function, and each local loss depends on the local data distribution. So this is how the algorithm progresses. At each client, in parallel, you run a descent step and an ascent step, and you do it repeatedly for say tau number of iterations. And then after tau's local steps, you average the model. Averaging basically means you send your local model to the server will aggregate and send back the average. And this process is repeated. So the first two steps are what is happening locally, and the averaging happens with the server. So let's look at the assumptions we need to do some theoretical analysis around this algorithm. First, we assume that each local loss function of all the clients is a smooth function. It essentially, I'll define it formally in a bit, but it essentially means you change the input by a bit, the function value changes by a bit. Also, we impose some, so the minimization variable. In the minimization variable, the problem can be as general as possible. It can be a non-convex problem. But in the max variable, we impose some amount of structure, and we can go into the reasons if someone is interested. So we impose some amount of concavity in the max variable y. So we either require strong concavity or just concavity. Later we look at a few more general assumptions, but we require some structure in the max variable. As far as the local updates at individual clients are concerned, we assume that the stochastic gradients which the clients use, they are unbiased estimators of their local gradient. So the stochastic gradient at the ith client is an unbiased estimator of the local gradient of the ith function. And these unbiased estimators are bounded variables. This is a standard assumption in federated literature or optimization literature. And because clients are doing multiple local steps, so we need to somehow make sure that they don't get too far from each other. We need to assume some kind of boundedness. So the assumption which is usually made is that the local gradients are not very different from the global gradient. So gradient of fi is the gradient of ith client, and this is the global gradient. So we require for all the clients, the local gradients are not too different from the global gradient. You can get rid of this assumption by doing something extra, but that is like this.
You are measuring data heterogeneity in terms of this gradient, how dissimilar these gradients are.
Yes.
Is this a good assumption?
So the question is that is this bounded heterogeneity in terms of gradients a good assumption? So that's a good point. So this is a standard assumption which is made in FL literature. It's not a good assumption in the sense that this is a bit technical, but with this assumption, you make very conservative, you get very loose bounds. So in practice, what has been observed is that you don't need this assumption, but so for, like this is actually a good question to consider, good theoretical question, that how do you get rid of this assumption and impose some kind of heterogeneity on the data itself. So this is actually not exactly on the data, but on the gradients, the loss functions. Okay? So yeah, this is not a
new measures to capture this heterogeneity.
sorry.
Are there new measures except for this gradient dissimilarity? Are there new measures?
So there is one paper I'm familiar with from last year which showed that this is a loose assumption. They proposed something, but like it was a heuristic kind of measure. But ideally, you would want some assumption on the data itself. For example, like you can have some bounds on the Rascher's time distance between different distributions. That would be something which would be better than this, but that is so far like nobody has been able to do it. That's a good question. Okay, so just to make the bounded heterogeneity assumption a bit more concrete, as I said, we are essentially assuming that if FIs are the local losses across at the ith line, then the FIs are not too different. That's how essentially the gradients are not too different. So I introduced a bunch of assumptions like smoothness and concavity in the last slide. So let's formally define them. So if a function is smooth, it means that at every point you can upper bound this function with a quadratic. Okay. Similarly, if a function is strongly convex, it means so if this constant mu is 0, then the function is just convex. If it is greater than 0, it's strongly convex. Strong convexity means that you can lower bound the function by a quadratic. If the constant is 0, then you can lower bound by plane. So this is the things which I said in figure. Yeah, so you can lower bound the function by a quadratic. If it is convex, or if it is strongly convex, you can upper bound it. If it is smooth, and if it is strongly convex, that means if the constant is greater than 0, then the thing to remember is that the function has a unique minimizer. That's the only thing you need to remember for this talk. And because we talked about concavity, not convexity, so the relation is that the function is concave, the negative of the function is convex. Okay, so because we are talking about min-max problems, and I said that in the min variable, the function is just smooth, it can be non-convex. So let's look at some notions of accuracy of the point. So we have a smooth function. Let's assume that the function is strongly concave in the max variable. In that case, if you, for a fixed x, for a fixed min variable, if you maximize the function, you will get a unique maximizer because of strong concavity. Therefore, if you define a function phi, which is just a function of x because you have maximized over y, then this is a well-defined function. Right? And it is also smooth. So what you end up with is if you try to minimize the function phi, it's a smooth minimization problem. And therefore, what we want to find is a stationary point of this function phi. So once we have that stationary point, we can. So in Minimax problem, you might have heard of something called saddle point. You don't have the same notion for in case of non-convex problems, but it's something similar. So we can go into more concrete details if someone is interested. But this stationary point of the function phi gives you something close to saddle point, quote unquote. So for this class of function, let's look at our results. This was a paper from ICM in 2020 in which they analyzed this problem for a single region. We consider a simple minimax problem, where in the min variable it was non-convex, in the max variable it was strongly concave. And this was the complexity they achieved. This complexity is optimal in epsilon. However, for this algorithm, you need a very large batch size. And actually, if you consider a constant batch size in this paper, you get a strictly worse rate. And it's for a single time, so no local updates. In AI Stats 21, these folks try to extend it to the federated setting, but the results are quite good. As you can see, if you choose n to the 1 here, then you don't recover the result of the first, you don't recover the first result. We proposed, we analyzed the local SGDA algorithm in this paper from ICML last year, and we were able to recover the initial results. And because we considered a federated algorithm, we also achieved some communication savings. So you might think that this can be larger than 1 over n epsilon to the 4 for some values of n, but there are some assumptions in this result, so this is actually similar. So you are getting some communication savings. This is, as I said, the result. The complexity result is optimal in epsilon. You cannot improve it. We were able to achieve this with a constant batch size. So in practice, if you have an algorithm which uses very large batch sizes, in practice it doesn't perform well. So it is crucial to get an algorithm which works with a constant batch size. And because of that n in the denominator, if you have n clients running the algorithm in parallel, you get some advantage. So this is called linear speedup in FL literature. In our subsequent work, we were able to improve the number of rounds or the communication cost from epsilon cube to epsilon square, and this is optimal. So now both the sample complexity result, number of iterations, as well as the number of communication rounds you have to do is optimal. You cannot improve this any further, at least in terms of epsilon. So to summarize the result, when you have a Minimax problem where the function, the global function, is strongly concave in the max variable and it's smooth across all the times, then under standard assumptions which are taken often in literature, local SGDA algorithm converges to an approximate solution, meaning the approximately stationary point of the function phi we saw, where a constant batch size and the algorithm is optimal in terms of epsilon in both the gradient complexity as well as the communication cost. So let's generalize this to a few more function classes. So suppose your function is no longer strongly concave, it is just concave in the max variable. In this case, the notion of stationarity is slightly more involved because if you maximize the function for a fixed x, you might not get a unique solution. Therefore, this phi function which we have defined, this need not be smooth anymore. So you don't get a smooth minimization problem. So we define stationarity in terms of a surrogate function phi of lambda. And this phi of lambda is a smooth approximation of the original phi function. So phi is non-smooth, but phi of lambda is smooth. So for those interested, there is actually a Monroe envelope of the original phi function. It's a smooth approximation of phi. And now you can define stationarity because now you can compute gradients. So you want the gradient to be smaller than epsilon. Lambda is a parameter you have to choose, and it depends on the smoothness of the original function. So exactly if your smoothness parameter is n, then lambda you can choose to be 1 over 2n or smaller. Okay, so let's look at the convergence results again. The same paper from ICML 2020 which we initially saw showed some complexity result, but there was no local updates here. And then another paper tried to extend to the federated setting, but the results were quite loose. So we were able to generalize it to the federated setting. Again, you see that n is the denominator. So if n is 1, it reduces to the original result. And we get some communication settings. Not a lot, but 1 over epsilon to the 7 compared to 1 over n epsilon to the 8. So again, this is smaller. There are some assumptions which make sure this is smaller. But this is not a lot. This is a very minor communication savings. So in our subsequent work, we are able to improve the communication savings by a lot, from epsilon to the 7 to epsilon to the 4. So this paper is actually, we uploaded it on archive last month. But there are certain open questions remaining here. So in the last function class, when there was strong concavity, I mentioned that you get optimality in terms of epsilon. Here I don't make any claims of optimality. And there is actually an open problem that even if n is 1, even if you are solving it at a single location, what is the optimal complexity for this function class? So that's an open problem. We know that it is no larger than epsilon 1 or epsilon to the 6. So all these results are actually loose. But what is the optimal is not known so far. Also, how to achieve this using a practical algorithm. This is also an open problem. The existing algorithms which achieve this, they're quite involved in double or triple loops, very intricate batch size choices and so on. So how to come up with an algorithm which is actually applicable in a standard machine learning application, that's an open problem. We are actually working on it right now. Okay, so let's get rid of concavity for now. We looked at strong concavity, let's get rid of concavity and go to non-concavity. So there is a class of functions called Kodiak coercive, and those familiar with neural networks might have heard of it. It's a generalization of, it's something like strong with concavity, but over non-concave functions. So you can go into more details if someone is interested. But this is slightly more general class, and this is actually observed in a lot of neural network applications. For this class of functions, we again repeated this exercise. The good thing here is that for this class of functions, actually we were the first to derive the complexity even for n equal to 1. This is again from the ICM paper last year. Then we generalize a bit more. And we looked at something called one-point concave functions. So again, this is an assumption, this is a technical assumption which has been observed for neural networks. And again, we repeated the same exercise. And further, so far we were looking at a very specific kind of algorithm. So this is the algorithm, local SGDA we were looking at. And you would notice that this was running at each client, at each of the n clients in parallel. But in the beginning, I said that you won't have all the clients available all the time, right? So we generalized it when only some clients are running the algorithm. Also, here we require all the clients to run the same number of local steps. But this might not happen in practice. So, as I said, we did partial time participation. We also generalized that every client can run a different number of local updates. You can have a small number of clients participating, all of them running a different number of local updates. And finally, this is a very specific algorithm we discussed, that you have SGDA running on all the clients. But we have further generalized to the case when different clients can run a different algorithm altogether. They can run a different number of local updates, they can run a different algorithm altogether. So everyone uses a different local optimizer, which makes sense because there are different kinds of devices. So different devices have different capabilities. So we have a smaller number of clients participating, the participating clients running different number of local updates, and running a different optimization algorithm altogether. I mean, there are some restrictions on the algorithm, it has to be a first order algorithm, but very minimal restrictions. Yes.
So how are you choosing your learning rates, eta x and eta y?
Eta x and eta y. Yeah, so the question is how are we choosing the learning rate? So in the convergence analysis, like as happens in optimization theory, you get certain constraints on the learning rate. The most concrete thing I can tell you is that the min variable learning rate, eta x, has to be much smaller than the max variable learning rate. So a bit more detail. So if you have strongly concave problem, minimization non-convex, maximization strongly concave, then you will have a condition number, right? In that case, your learning rate should be at least 1 over condition number square times smaller for the main variable compared to the max variable. And this is also actually an open problem to get rid of this bound, because this bound you observe across the board.
Condition number will come if you have the total data set at that place, right?
Sorry?
The condition number you find.
Yeah.
Ultimately, the maximum eigenvalue will be the Lipschitz also.
Yes.
And minimum will be the Pranay.
Yes.
So you are getting condition number. But you need to get the full data set to get the condition.
You assume certain bounds. Yeah. So the question is that what is the best ratio? Like as I said, it is one more condition per square. So is square the optimal choice, or can you get linear or even square root? What is the optimal? That is no question. Because essentially we are saying that your min variable should be updated at a much smaller rate compared to the max variable. While in practice, for example, in GANs, you choose almost the same learning rate. So why is this coming? This is there is some partial answer to this again from ICM last year. But what is the optimal ratio? Can you choose the same learning rate? That is again an open question. So just to summarize, we are trying to solve a Minimax problem in the federated setting. We have n clients, and we considered a bunch of classes of functions. In all those classes, the functions were smooth. So in the min variable, the problem is non-convex. In the max variable, it can be strongly concave. It can be polyactive SFH. It can be concave, or it can be one-point concave. And we analyzed SGDA-like algorithms, stochastic gradient descent, ascent, like local algorithms. We are able to run these algorithms with a constant batch size. We were able to show the theory for it. And we showed that if you run the algorithm in parallel at several agents, you get some speed up out of it. And the complexity results we have, they are either optimal for the classes of functions shown in brown, or they are state of the art for the classes of functions shown in purple. So this was the first challenge, solving Minimax problems. Now we move on to the second challenge. Like how do you solve cyclic client participation? How much time do I have?
10 minutes.
Okay. I thought I'll have 3 hours. Okay, no worries. So let's look at cyclic client participation. This was a work we uploaded on archive in February. So this is a joint work with several people. EAG is a graduate student at CMU. Obviously my postdoc advisor, and folks from Google, Zen, Saket, and Tom. So again, let's look at the same schematic we have already seen twice. So we have a specific round in federated learning where a few clients are selected by the server. The server sends its global model. There are local updates, they send back their local updates. The server aggregates them, arrives at a new global model, and the process repeats to the different set of clients. This was the schematic we saw earlier. But what if there is some amount of structure in how the clients are distributed? So this is your entire set of clients. Now, they may be divided into some number of disjoint groups, as we saw in the example of those time zones, right? So say we have, so we have G client groups, and the server has to go through all the G client groups in a sequence, 1, 2, 3, and so on, and the process repeats. So how a cycle, so earlier I was talking about rounds. One round meant communication between the server and the client once. Now I'll talk about something called a cycle. Cycle means going through all the client groups once. So we start with the first client group. The server selects a few clients, the larger devices. They're just like they're not actually larger. They are the ones selected. So the server sends its global models to these selected clients. They do local updates. Then they send back their local updates to the server. The server aggregates these to come up with a new model. This all is happening with the first client group. Then the server moves on to the second client group, repeats the same process, and so on. It moves to the third and so on, the last client group. This is one cycle of the process. And once it has gone through all the G client groups, the one cycle is complete and you move on to the next cycle. So what is the kind of convergence error? If we have this fixed structure, fixed order in which you need to go through client groups, you cannot uniformly randomly pick from the entire set of clients. So now we are solving a simpler problem. We are solving a minimization problem. This is no more Minimax. And your global loss again is an average over n local losses FIs, where each local loss depends on the local data distribution D. Here we assume, for the sake of this talk, that actually smoothness we assume always, but so all the local functions are smooth. For this talk, we assume that the local function is strongly convex. We have other results, but it's in the paper. So this is the convergence error we get, and I'll let you stare at it and get it evaluated for a second. I'll let you think about it. So let me parse all the terms. This is quite a lot. So the first term, order 1 over t n t square, is the number of clients, t is the total number of cycles we run. This is the initialization error. So in machine learning, we have bias variance trade-off. So this is just dependent on where we initialize, where we start our algorithm. This is just the initialization error. The second term is something called sigma intra-client. So this is intra-client variance, in all often denotes variance. So this is intra-client variance. So what I mean by that is that heterogeneity of clients local data. So suppose you are one client, you have a small amount of data. What is the variation within your own data set? Right? So how much your local data, how much is the variation in your local data? This is captured by the intra-client variance. The next term is intra-group variance. It depends on intra-group variance. So as can be imagined, it depends on, you look at the client group as a whole. Each client group has its own small data set. And how different are all those local data sets from each other? Right? So this is again the animal classification example, and different people have different images of animals, and how are they different from each other in some sense. We are actually talking about difference in terms of gradients as we did earlier, but intuitively that's what we mean, difference in terms of data. And the last term is how different are the groups from each other. So what is the intergroup heterogeneity across groups? So suppose we have data, or we have an animal classification application, but the data across groups is of different kind. For example, the first group only has paintings of animals. The second group only has sketches of animals. Another group has actual photographs of animals. So there can be variation across the client groups also. So how different is data across client groups is captured by this last term. So essentially we have dependence on initialization, we have dependence on variation within a client, we have dependence on variation within clients within a group. Variation across clients within a group. And lastly, we have variation across groups. Right? Yes.
So the second term comes because of the batch selection.
The second term.
Performing a Minimax is
Yes.
If you perform a GD,
yes.
then it will be better. So the second term should consist of the batch, the batch size, right?
So in this work, we actually assume the batch size of 1. That's why, but you will get the batch size. So the question was that the second term should depend on the batch size, and it does. We just for this analysis we assume the batch size of 1. That's why. Otherwise, you guys must have a B for B batch size. Yeah. Okay, so let's look at a special case because this expression is a bit complicated. And one more thing I should mention. So for simplicity, I have assumed that when the server is looking at a specific group, it is selecting all the clients from that group. It is not subsampling within a group. It is actually selecting all the clients. I think I have one slide in which I have the error when actually it samples within a group. So suppose you have a single client group, which is the standard federated learning setting. You have a single client group, you select from this entire batch of clients, and you select all the clients. Right? In that case, the last term goes away because there is just one group, so there is no intergroup heterogeneity. And you can simplify this complex expression quite a bit to the blue expression. So you get something like this. Like tau is the number of local updates the clients done, n is the number of clients, and t is the number of cycles. Right? Now, as I said, this is the standard federated learning setting. And if you look at the existing best bound in this setting, then this is the one on the right. And as you can see, in the second term, we get an additional n in the denominator, which the existing bound doesn't. So we actually end up getting a better bound for an existing setting. And because you have a better bound, so you can, I can explain this more, but one line I would say is that you can choose a larger tau. So you can run larger number of local updates, which helps you save on communication. So we can generalize this. This was a very specific setting. We assume that within a client group, you are selecting all the clients. Okay? We can generalize it further. So the bound which you saw was when everyone was running SGD. They were running tau steps of SGD on their own, but you can run something else. So as you mentioned, you can run GD, which that term will disappear, or you can run something called shuffled SGD. So shuffled SGD, very quickly, this is actually the more interesting part of the work, but more important, so I didn't include it here. But shuffled SGD is essentially, instead of at every iteration, instead of picking some samples uniformly randomly from your data set, you go through your entire data set in a sequence. So there is some similarity. The server is going through all the client groups in a sequence, and the client is going through all the samples in a sequence. And this is actually what happens in practice. But for simplicity, for a long time, people assume for theory that you uniformly randomly sample your examples. Right? But there is some recent, by recent I mean starting 2019, in which this shuffling thing has been analyzed. There are some quite interesting results here. We analyzed shuffled SGD locally at the clients, and there are some interesting results there. And we also generalize it to the case where within groups you can subsample some clients rather than the entire group. And with that, so earlier we had the terms at the top, the 4 terms at the top. Now we get one additional term. And among the terms at the top, there are a few changes. So wherever you see a blue color term, we have actually replaced n with the number of clients, n over g with the number of clients participating. So we call it C, which is understandable. And another thing to notice here is, so this is, okay. So in first, third, and fourth term in the top line, you see a 1 over t square. Right? In the second term, you see a 1 over t, but that also has a tau in the denominator. Right? But in the term at the bottom, you just have 1 over t. So if all these 3 kinds of heterogeneity are similar in magnitude, in that case, the fifth term is actually the dominant term. So the partial participation of clients within a client group is actually the most significant source of error. And this is actually consistent with standard FL theory also. This is observed in standard FL theory also. So this last slide was messy, but to summarize, uniform client sampling in federated learning is done in theory, but it's not always feasible. So we analyzed slightly more realistic settings, where you have cyclic client participation. But there are several open questions here. So in experiments, we saw that if you partition the clients into multiple client groups, then you get some benefit in terms of experiments. But in theory, we haven't been able to show that. The cost incurred, the theoretical cost is actually higher when you choose a larger G. So we are still trying to figure this out. Another question is that the bounds which we have, are they the best possible bounds? Can they be improved? What are the lower bounds? In some special cases, we have been able to match the existing best bounds or the existing lower bounds, but in the most general setting, what is the best bound is open. And lastly, what is a even more realistic client participation setting? So here we kind of impose a very strict structure that you have a bunch of client groups and the server has go through them in the exact same order. But you can have a more realistic client participation setting. I can talk briefly about that as well if there is some question. But yeah, so this is the summary of this question. There is some other work I have done. I will quickly skip this. So this is on federated learning and on some on reinforcement learning. If there is some interest, I can talk about it offline. But to conclude, we considered federated learning, and we considered two challenges or questions there. How do we solve Minimax problems rather than simple minimization problems? And how do we solve a more realistic client participation setting rather than uniformly sampling clients? How do we consider cyclic client participation? For Minimax, we considered SGD-like algorithms running locally at the clients, and we were able to do some theory around it. We were able to show convergence with a constant batch size. We were able to show benefit of running updates in parallel at multiple clients, and our complexity results are optimal or state of the art, depending on the function class. For cyclic client participation, we were able to generalize it to partial client participation. We were able to improve some of the existing known bounds, and we considered multiple kinds of local updates. You can run gradient descent, stochastic gradient descent, or shuffling based SGD. That's all I have. Yes.
So, considering practically, like it's shown that that O and it depends on its dependence on N.
Right.
So, like if you increase the devices, your error will go down.
Right.
So it means that we, as a user, can actually decide that this much percentage of error in the actual model is required, and it can actually select N according to that. Is it?
So N is the number of users. Do you mean so? Let me understand the question. So do you mean that the server can decide what is the required number of users and then choose the users accordingly?
The number of that N it can decide.
How many people will download that app? Right? They can have an upper limit, but that's it. So that is one part. The second part is if you have partial participation, then yes, you can choose that I will allow larger number of local updates. But there are some physical constraints there that there can be latency issues if you have too many number of users running in parallel. Yeah, and the number of users participating is also always not in the server's control. So this is slightly beyond the server's control because not too many devices can be on Wi-Fi and getting charged. So the availability of devices is not always under the server's control. It is quite application dependent. In some cases the server can ensure, in some cases it cannot.
Like my question is like it can N will affect the error term.
Yes.
Like,
yes.
and so
Not all the times, yes, but sometimes. Yes.
sometimes it will actually define and so can okay. So in using a server cannot have that capability to decide the N.
So
That's so it cannot actually directly decide the error that I require this much error.
yes.
So I can't decide the user.
Yes, so you're saying that the server cannot. So first, for this favor, for this analysis, we just assume that n is fixed. You are given some n, and then this is your error. Right? But we are asking what happens in practice. Can the server control n? Can it control the number of clients participating? So that is a different volume altogether, and I don't claim much. I cannot claim much about this. How relevant this result is in practice, because again, as I said in the beginning, so let me rephrase, I shouldn't miss my result like this. But so our assumption, the heterogeneity assumption, that's dependent on the gradient, right? So it's a very loose bound in that sense, right? Compared to what will happen in practice. So this is just an indication of what are the kind of terms you should focus on. So just to give you an example, this is a slide aside. But for a long time in federated learning, people were focusing on the heterogeneity because of data, difference in data across devices. And there were lot of approaches to address that. Right? So one of the oops. So in this work actually we showed that under certain conditions, partial participation is actually the most significant source of it, rather than data heterogeneity. So it things are a lot more subjective depending on the kind of federated learning application you are looking at. The theory is just an indicator of some under some assumptions what are the bounds you can take. But those assumptions might not be realistic like the heterogeneity assumption we just mentioned. There's a question in the chat. So the question is related to cyclic client participation. How does three sigmas appearing in file and convergence and bounded heterogeneity parameters C related are the bounds dimension free? Yes, the bounds are dimension free, but the caveat there is like you might have dependence on dimension on the smoothness parameter. So we do have dependence on the smoothness parameter, but other than that, the bounds are dimension free. How are the sigmas appearing in final convergence and bounded heterogeneity parameters C related? I'm not sure I understand the question. Maybe you can unmute yourself. What I understand is like C is the number of clients within a group is the server size. It is not related to heterogeneity. Maybe maybe you can ask.
Hello. Hello. Am I audible? Hello. Am I audible?
Yes.
Okay. Yeah. So you had this bounded heterogeneity parameter, right? I think you had seen your earlier slides. If you can go back to that.
Okay. How should I go to the issue?
No, the point where you made the assumption, I think the assumption slide.
Do you mean the Minimax part?
I am not sure. Oh, I see. Yeah. So So how do you have the assumption here about the bounded heterogeneity in this setting?
Yes. So all these sigmas, so let me go to the full bound. Yeah, so all these sigmas are actually bounds on how different gradients are. So for example, the heterogeneity local data. This is how different the gradient for each sample is from the gradient of the local loss function. Similarly, the intra-group heterogeneity. This is bound on how different the local gradients are across devices within a group. And the inter-group heterogeneity is a bound on how the group gradient, the gradient of an entire group, how are they different across different groups. So these are all bounds on the gradients, or bound on how different the gradients can be. Did that?
I see. Thanks.
The slides and the video will be updated in the web page.